Let us start NCERT CBSE class 10th mathematics exercise 1.1. Here the first question is use Euclid division algorithm to find the HCF of 135 and 225. Here first of all we see which number is greater. The greater number will be taken as a dividend and the smaller one will be taken as divisor. Here 225 is the dividend because 225 is greater than 135. Therefore 225 is dividend and 135 is divisor. You see, normal division, which we know already, is like this. If you divide this, the quotient will be 1. Again the remainder is 90. You see, the 90 is smaller, or 135 is greater than 90, or 90 is remainder is smaller than the divisor. So again this divisor will become dividend and the remainder will become a divisor. So again the quotient will be 1. Now remainder is 45. Now the previous divisor will become dividend. So here 90 is dividend and 45, that is preceding remainder, will be divisor and the quotient is 2. Now the remainder is 0. Hence the process is stopped here and the last divisor is taken as a HCF, and this can be illustrated by using the Euclid division algorithm to find the HCF. You see, I have written here 225 will be equal to 135 into 1 plus 90. Again this 135 will be equal to 90 into 1 plus 45. Now this 90 will be placed here. 90 is equal to 45 into 2 plus 0. So the last divisor is will be the HCF of the given two numbers. Similarly, we can proceed the second question, that is 196 and 38,220 is the second number. So in this number we will see which number is greater. So 38,220 is a greater number and 196 is smaller. The smaller will be taken as a divisor. You see, I have done first of all normal division process. So here the quotient will come 195. You see, I have divided it. So 196, again the remainder is 186. You bring 2 here, and after that again you divide by 9, multiply by 9. So you will get 98 as a remainder. So bring 0, and so it will be 980 will come when we multiply by 5. And this number can be shown like this. 38,220 is equal to 196 into 195 plus 0. So the here HCF means the last divisor. The which was the last and initial divisor both are the same. So the one number that is 196 is itself the HCF of these two numbers. So hence the HCF will be 196. Now proceed to the third part, that is 867 and 255. That gives you that 867 is greater than 255. So first of all we will start with that division algorithm theorem. Just apply it here. So 867 will be equal to 255 into 3 plus 102. This will be the remainder. Now 255 will be taken as a dividend and 102 will become divisor. So 102 into 2 plus 51 will be equal to 255. Now this divisor will become the dividend and the remainder will become divisor. So the 51 into 2, and again here you see that the remainder is 0. Now last divisor is 51. Therefore the last divisor will be the HCF of 867 and 255. That is 51. Meaning HCF of 867 and 255 is 51. This will be the answer of the third part of the question number 1. Now proceed to the question number 2. So that any positive odd integer of the form 6q plus 1, 6q plus 3, 6q plus 5, where q is some integer. Before proving, let us take any odd positive integer. Say 3697. Just I have taken a bigger number and start dividing it. So we will get 616 and 1 by 6. So this number means 3697 can be expressed in the form of 6 into 616 plus 1. So under 1 I have written R1 means remainder, and here 6 on 6 will be the quotient and 6 is divisor. So this odd number, I have taken many example to illustrate it. You see, I have taken 7 as an odd number. So divisor is 6 here, the quotient will be 1 and remainder will be 1. This can be written in the form 6 into 1 plus 1. In the second case I have taken 21 as a odd positive integer. Divide it by 6, the quotient will be 3, remainder will be 3. So the 21 can be written in the form 6 into 3 plus 3. Now take 35. So 6 into 5 means divisor is 6. In all cases the divisor is 6. The quotient can vary accordingly. So 5 is the quotient and remainder is 5. Now you see 35 will be equal to 6 into 5 plus 5. Now take 47. That is the odd positive integer. So 6 as a divisor, 7 will be quotient and remainder will be 5. So 47 can be written 6 into 7 plus 5. Now take the another example, that is 51. 6 divisor, 8 is quotient, 3 is remainder. So this 51 can be written. This complete form is written in the form of Euclid division algorithm. So 51 can be written 6 into 8 plus 3. Now 67, 6 into 11 plus 1. So 67 will be equal to 6 into 11 plus 1. So you see in this form you will get 6 into either 6q plus 1, 6q plus 3, 6q plus 5. You see here 6 into 1, here q is 1, 6 into 3, that is q is 3 plus 3, 6q plus 3, 6q plus 5. You see in all these cases we are saying, we are getting that 6 into 1 plus 1, 6 into 3 into plus 3. So in all cases you see either it is remainder is 1, 3, 5, 5, 3, 1. You see I have taken this example to make you understand so that we can proceed if the taking the now see the multiple of 6, which questions we have proved earlier. Multiple of 6 is 6, 12, 18, 24, 30, 36, 42, 48, 54, 60 and so on. It is not a table, it is a multiple I have seen written here. So add 1 or 3 or 5. You see in here the remainder, set of remainder is 0, 1, 2, 3, 4, 5. Means the possible chances that the remainder will be 0, 1, 2, 3, 4, 5. Means it will be less than or less than 5. Less than 6. Remainder will be always less than 6. That is the remainder always less than divisor. Here divisor is 6. Hence, from the above example, it is proved that any positive odd integer can be expressed in the form of 6 cube plus 1 or 6 cube plus 3 or 6 cube plus 5. When the divisor is 6, set of remainder is 0, 1, 2, 3, 4, 5 means less than 6. So remainder will be always less than 6. So that can be also written in this form: 0 is less than or equal to remainder and remainder is less than 6. If remainder is 0 to 4, in case when the remainder is 0 or 2 or 4, the dividend will be positive even number. Positive even number. And when the remainder is 1, 3, 5, this gives the information about the dividend. The dividend will be positive odd number. So let us proceed to the question number 3. Question number 3, 616 and 32. You see the question number 3, just I am reading it. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of the column in which they can march? So just here we have to take the HCF of these two numbers. Now you see 616 has been divided by 32. The quotient will be 19 plus 8. Again this 32 will become dividend and 8 as a divisor, so 8 into 4 plus 0. So here the last divisor is 8 and the remainder is 0. So therefore the HCF will be 8. Means highest common factor of these two numbers is 8. Therefore the maximum number of column will be 8. This will be the answer. Now proceed to the question number 4. Question number 4. Use Euclid division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So before proceeding to prove it, let me illustrate with the numerical data. Here I have taken the positive integer 1, 2, 3, 4, 5, 6 and so on. The square of these numbers I have mentioned here. Now let us proceed to see that how it can be written. Either it will be in the form of 3 into m or 3 into m plus 1. So we just see that this square can be written in the form of 3m or 3m plus 1. Let us see here. Here you see 1 can be also written as 3 into 0 plus 1. Now see 0 is integer. Now for 4, that is square of 2 is 4. So 3 into 1, 3 plus 1. Now the value of m is here 1. You see 3m plus 1. So the value of m is 1 here. So 3 into 1 plus 1, that will be equal to 4. Now in the third case, the square of 3 is 9. So 9 can also be written in the form 3 into 3 plus 0, means 3 into m. That is, the value of m is 3 here. Now proceed from square of 4 is 16. That 16 can also be written in the form of 3 into 5 plus 1. Now proceed for 5, the square of 5 is 25. So 3 into 8 plus 1. So in this case here we are just seeing that these values are the value of m. And this is 3, that is divisor. And these are the value of quotient, which is an integer. And these are the remainder. You see, in all cases we are just getting either it is 0 or 1. Here 3 is a divisor, therefore the set of remainder will be 0, 1, 2. Either it will be 0, 1, 2. Say x be any positive integers which can be expressed in the form of this. So x, see, you see here 3q plus 0. Here remainder is 0. 3q plus 1. Here the remainder is 1. 3q plus 2. Here remainder is 2. And possible set of the remainder is 0, 1, 2. Here I have written. Any positive number can be expressed in this form, either from this or this or this. So take the square of x. So accordingly we have to take the square of these numbers. Let us take the square of this 3q. It will become 9q square plus 0. Here you take the square of this 3q plus 1. So it will come 9q square plus 6q plus 1. Now here this we can take out 3 common. So inside the bracket we will get 3q square plus 2q plus 1. Now here you see this 3 stands for 3 divisor, and the value of m will be equal to 3q square plus 2q. Inside the bracket the value of m is mentioned here. Here I have written it also 3m plus 1. It will be in the form of 3m plus 1. Now 3q plus 2, you can take if any number which can be expressed in the form of 3q plus 2, if you make the square of it, you will get 9q square plus 12q plus 3 plus 1. You see, when you will get the square of 2, that I have already written here, in place of 4, 3 plus 1. So take out the 3 common. So we will get inside the bracket 3q square plus 4q plus 1, bracket closed, plus 1. So again you see 3m plus 1. Here m stands for the 3q square plus 4q plus 1. So it is an integer. You see here, first 3m plus 1, 3m plus 1. M is equal to here 3q square. Here m is equal to 3q square plus 2q. Here m is equal to 3q square plus 4q plus 1. Hence it is proved that any positive integer can be expressed in the form of 3m or 3m plus 1, where the value of m vary accordingly. जो इंटीजर्स की वैल्यू है, m की वैल्यू है, that will keep on changing or varying. Now question number 5. Use Euclid division lemma to show that the cube of any positive integer is of the form of 9m, 9m plus 1, 9 or 9m plus 8. I repeat the question again. Use the Euclid division lemma to show that the cube of any positive integer is of the form 9m plus 9m plus 1 or 9m plus 8. Here I have mentioned here, the question is already written here also. You see, I have taken the first of all numerical value, let 1 cube, that will be 1. So here this number can be also expressed as 9m plus 1. So here m is equal to 0. When you multiply 9 with 0, it will become 0, so plus 1. Here the cube of 2 is 8. So 9 into m plus 8. Here m is equal to 0 and plus 8. Now come to 3 cube, that is equal to 27. That can be also expressed in the form of 9m, where m stands for 3. 4 cube, that is 64. That can be expressed into 9 into 7 plus 1. So the value of m is 7. M is equal to 7. Here 5 cube is equal to 125. So it can be expressed in the form of 9 into 13 plus 8. See, 39 is 117 plus 8, 125. So m is equal to 13 here. So 9m plus 8. It is in the form of 9m plus 8. Now take the cube of 6, that is 216. So 9 into 24 plus 0. Here m is equal to 24. So it is in the form of 9m. Take the case of 7 cube, that is 343. So it can also be expressed 9 into 38 plus 1. Here m is equal to 38. So 9m plus 1. You take the case of 8 cube. So 512. So 9 into 56 plus 8. So m is equal to here 56. So 9m plus 8. It is in the form of 9m plus 8. Take the case of 9 cube, that is 729. It can be also expressed into 9 into 81. Here m is equal to 81. So 9m. You take the case of 10 cube, that is 1000. 1000 can be expressed 9 into 111 plus 1. Here m is equal to 111. So it is in the form of 9m plus 1. Now this statement is in the form of numerical data. Let us proceed some theoretical part of it. Let a be any positive integer and b is equal to 3, where remainder will be 0, 1 or 2. Either 0 or 1 or 2, because it should be less than 3. Here divisor is 3. See, by Euclid division lemma, a is equal to bq plus r, where r is 0 is less than or equal to r and r is less than b. Here a is equal to 3q plus r. When r is equal to 0, At that time, a will be equal to 3q plus 0. Take the cube of both the side, left hand side and right hand side. You see a cube and you take the cube of 3 cube, it will be equal to 27 cube. This 27 cube can also be written in the form of 9 inside the bracket 3q cube, and that is in the form of 9m. Now proceed. When r is equal to 1, at that time that number can be expressed in the form of 3q plus 1. Take the cube of these two, left hand side and right hand side. So left hand side you will get a cube, on the right hand side 3q plus 1 whole cube, it will be equal to 27 cube plus 27 cube square plus 9 cube plus 1. You take out 9 common, you will get inside the bracket 3 cube is cube, 3 cube cube plus 3q square plus q, bracket closed, plus 1. So 9m plus 1, it is in the form of 9m plus 1, where m is equal to 3q plus 3q square plus q. When r is equal to 2, at that time a will be equal to 3q plus 2. Taking the cube of both the side, on the left hand side we will get a cube, on the right hand side we will get 3q whole cube plus 3 into 3q का whole square into 2 plus 3 into 3q plus 2 का square plus 2 cube. Further solve it, you will get 27q cube plus 54q square plus 36q plus 8. Now here you take 9 common, so inside the bracket we are left 3q cube plus 6q square plus 4q, bracket closed, plus 8. So it will be equal to 9 into m plus 8. It will be in the form of 9 into m plus 8. So all these numbers, these data and information proved that any number can be, whose cube can be expressed in the form of 9m, 9m plus 1, 9m plus 8. I have proved it numerically also, and theoretical part also I have mentioned here. That's all.